This is our lab lecture video for the synthesis of triphenyl methanol, right? One carbon, the hydroxyl group, there's methanol, and we have 1, 2, 3 phenyl groups. We're going to synthesize this using a GRIGNARD reagent. A GRIGNARD reagent is a specific organomagnesium reagent that's used very often in the synthesis of alcohols. So a GRIGNARD reagent has a magnesium interacting directly with a carbon. And we make GRIGNARD reagents from alkyl halides, usually either alkyl chlorides or alkyl bromides. So magnesium, right, when we put magnesium in, and we put it in as magnesium metal, right, as solid magnesium metal, metals tend to act as Lewis acids. And so as a Lewis acid, right, magnesium has empty orbitals in its valence shell. The bromine, the unshared pairs of electrons with bromine can interact with that, creating a polar bond. But magnesium also has an orbital with a pair of electrons. So if those electrons transfer to the carbon, and as often happens, this bromine, because of this interaction, can become a better leaving group, the magnesium can become inserted between the bromine and the carbon. Now, what's really important about this is the polarity of the bonds in question. In the alkyl halide, and in alcohols and other reagents that we use, right, it is the functional group, which is the electronegative group, and the carbon is electropositive, meaning that in most alkyl halides, alcohols, other things we've worked with, the carbon is acting as an electrophile. But the important thing about an organometallic reagent in general, and in this case a GRIGNARD reagent in particular, is because magnesium, right? Magnesium is very electropositive, much less electronegative, more electropositive than carbon, right? Now, carbon gets to be the more electronegative thing in this bond. And so the magnesium becomes the electropositive thing. The carbon becomes the electronegative thing, which means now we've got a situation where carbon has control of these electrons in this bond, and that means carbon can now act as a nucleophile. It's something we don't see very often. The only other time we've seen this, at least in class, is when we used terminal acetylides as nucleophiles. Right? Some kind of metallic terminal acetylides. We use those as nucleophiles. So here we have another way of creating nucleophilic carbons in a way that's more flexible, right? In this, we're sort of limited to the alkyne group with our acetylides. The nice thing about GRIGNARDs is that GRIGNARDs will work with, if we start with an alkyl halide, the GRIGNARD works on sp3 hybridized carbons and sp2 hybridized carbons, right? So it'll work on alkyl halides, it'll work on vinyl halides, and it'll work on aromatic halides. It's a very flexible reaction. So we can create GRIGNARD reagents starting with a variety of organic halides to make organomagnesium compounds where the carbon can act as a nucleophile. That's very flexible chemistry. Now, one thing about GRIGNARDs, though, when we create that situation where the Grignard becomes, the carbon becomes the negative, right? Then we create a situation where that carbon becomes a really strong base, right? And so if there's something in there that's in any way acidic, right, that will become protonated. And instead of a useful Grignard, a hydrogen will replace our polar bond and create something that is relatively non-reactive. Non-reactive. Right? Once we put a hydrogen on these kinds of carbons, those hydrogen carbon bonds are not reactive. And so, this is a way, and we'll see it in class, if we want to replace a halide with a hydrogen, reacting a Grignard or an other organometallic compound with some kind of an acid is a way to do it. But that's not why we usually make a Grignard. Usually we make a Grignard to act as a nucleophile in some kind of other reaction. So we want to keep Grignards away from anything that might be protic. Water, alcohols, even amines. Right? The Grignard is a stronger base than an amide ion and will deprotonate amines. You'll notice I'm going to reinforce that idea. Right? So, we can't have any protic groups, right? We can't have any protic groups around. And that means in anything. We can't have protic groups in the solvent, right? We have to use aprotic solvents, right? We can only use aprotic solvents. We can't have any protic groups in other regions of the alkyl halide, right? If there are other functional groups in the alkyl halide, none of those functional groups can be protic. And then, right, any other substance in there, right, can have no protic groups. So whatever group that we're, whatever substance, whatever molecule, whatever compound we're trying to react our Grignard with, can't have any protic groups in another area of the molecule. All of those things will cause the Grignard to be protonated, and then it becomes unreactive. Okay? So, reinforcing this again, we can't have anything with a hydroxyl group, a thiol group, or a nitrogen-hydrogen group. No water, no alcohols, right? None of those kinds of things can be used as solvents. And, if we're trying to make a Grignard, here we have our halide, but there can't be a protic group somewhere else in the molecule, because when we make our Grignard, it will immediately react with that protic group to protonate that position, right? You get the idea? We're really serious about keeping protic groups away from Grignard reagents, right? Remember, right, Grignard reagents are negative carbon species, right? And we know that, right, acidity gets stronger as we go this way, right? Hydrofluoric acid is hydrogen bound to fluorine is a stronger acid than hydrogen bound to oxygen, right? So if we get stronger with acids going that way, we're going to get stronger with bases going that way, right? So base strength gets stronger. So, right, a negative carbon can deprotonate any of these other groups, right? Right? Any of these groups, even down here, right? So we have to keep hydrogen's bound to any of these atoms away from our Grignard. We can even include chlorine there, right? Okay. Now, once we've made our Grignard reagent, right? We talked about making our Grignard reagent, and we've created that situation where now, right, our carbon is negative and our carbon becomes nucleophilic. When we're making alcohols, we react our Grignard reagent with carbonyl compounds, particularly, right, for alcohols, aldehydes, or ketones. Right? We'll use aldehydes or ketones. Now, in an aldehyde or a ketone, right, the electronegativity of the oxygen pulls electrons toward the oxygen. It makes it negative. The carbon it's bound to is sp2, and it becomes the electropositive part of the bond. So that makes this carbon an electrophile, and the Grignard, being a strong base, is a strong nucleophile. Right? So our Grignard can attack, right, the sp2 hybridized carbon. The electrons from the pi system can move toward the magnesium, and the result is a new bond between oxygen and magnesium. This carbon becomes sp3, and we have created a new carbon-carbon bond, right? So using a Grignard reagent with an aldehyde or a ketone is a way of making a new carbon-carbon bond, right? And so we end up here with an alkoxy, magnesium, I can write today, bromide, intermediate, right? So you get an alkoxy, magnesium, bromide, intermediate, where you have this polar, or probably even really ionic, oxygen-magnesium bond. Often it's written as a complex, right? But we have, our magnesium is going to be positive, our oxygen is going to be the electronegative. Then, right, if we want to make an alcohol, we put in some aqueous acid, right? The alkoxide, right? The alkoxide can take the hydrogen ion, right? Water is released, right? The electrons there, the electrons in this bond become the electrons in the oxygen-hydrogen bond. Now we have completed our alcohol, right? This is our alcohol. And then we have a magnesium bromide salt left over, right? An aqueous salt that we can easily extract and separate from our alcohol. So that's the basic chemistry for using a Grignard reagent to synthesize an alcohol. Okay, so our specific Grignard reagent, right, we're going to use a phenyl magnesium bromide, right? So we're going to use the phenyl ring, right? And we know that, right, we're using the flexibility that we have here because our bromine is on an sp2 hybridized carbon. And I've sort of shortened the mechanism, but you can see the relative attacks, right? You can see the electrons from bromine go to magnesium. That allows magnesium's electrons to go to the bromine. right? The interaction of magnesium with bromine makes bromine an even better leaving group. It can leave, and the magnesium ends up being inserted between the carbon and the bromine. All right? So now we have our Grignard, right? Our Grignard can act as nucleophile to attack the carbonyl of our benzophenone, right? Our electrophile here is benzophenone. Right? Another name for this would be a diphenyl ketone. Right? So we get our attack. Whenever you attack a carbonyl, the electrons move and open that up, and we go from sp2 to an sp3 hybridized intermediate, right? That's standard whenever a nucleophile attacks a carbonyl. And so we've got our alkoxide, magnesium, bromide complex. Now we need to protonate it, right? If we put in, water with a little bit of acid, either sulfuric acid, what we're using here, sometimes hydrochloric acid is used in this step, right? Then the oxygen can take a hydrogen ion, and you end up with your protonated alcohol as your final product. It's a very straightforward reaction mechanistically. The challenge is, how do we do all of this and keep it away from water? Because at no time when we have the Grignard reagent can we have any water or anything else protic around, right? So one of the things that we do is we have to have a solvent. And in general, the solvent for these is an ether, right? In this case, we're going to use diethyl ether, right? Diethyl ether. The polarity of the ether works well with the polar nature of this part of the Grignard reagent, helps stabilize the Grignard reagent, and helps stabilize the intermediate during its formation. But the ether is also aprotic, and we can get ether that is anhydrous. That is, it has been synthesized and all the water has been removed. So we will use anhydrous diethyl ether as our source, or as our solvent for all of this. Now, another thing that we will do is that we will heat dry all of our glassware, right? So we are going to, when you come in, rather than flame drying, as the procedure says, all the glassware will be in the oven. And so don't use any glassware that wasn't in the oven. Don't pick up a graduated cylinder. Glass has a very polar surface, and just the water in the air will hydrogen bond to the surface of glass. So there's always a significant amount of water just on the surface of anything glass. We have to keep it in the oven to drive that water off so that we can do this. Now, this is the setup, right? So you see we're going to have a round bottom flask. In this case, instead of a 250, we're going to use a 125 milliliter round bottom flask because we're changing our amounts. Really read the newly posted lab learning goals, right? So we're going to use a 125 milliliter round bottom flask. Right? We're going to use this thing, which is called the Claisen adapter. It lets us it lets us attach two things to our round bottom flask. We're going to use a separatory funnel as an addition funnel, right? Since we want to keep, that's what I wanted. I wanted to erase that, right? Since we want to keep all sources of water, including the air, out, we're going to put, right? We're going to put our funnel, right? Our separatory funnel, and you have to use one that has a ground glass joint here, so that it can seal on the Claisen adapter. So anything that's going to end up in the round bottom flask, we put in the addition funnel, and then we can add it and not allow, not open our round bottom flask to the atmosphere, right? We're going to have a condenser, right? Because as we make this, it actually generates quite a bit of heat, and so it will reflux on its own, right? So we want our condenser set up to capture any of our vapors. We're going to put the thermometer adapter, the rubber thermometer adapter, on the top of these two straight adapters, and then we're going to put Pasteur pipettes with anhydrous calcium chloride in them. Now, calcium chloride is one of the things we can use as a drying agent, right? We've used those pellets as a drying agent for some of our liquids. We're going to do the same thing here, so that any of our, any air that gets in and is trying to get through the system has to pass over the calcium chloride, which will absorb any water. In the air. Okay? So all of this glassware will be in the oven when you come in. The oven will be hot, so you're going to have to handle it with gloves. Right? Don't forget, and burn yourself. Use the heat-resistant gloves as you set it up. Don't let any water touch any of the things coming out. And this should include, this is our setup, but it should include things like graduated cylinders, right? Graduated cylinders should be in the oven. Right? So anything you're going to use that's going to touch your reagent has to be heat dried. We are making modifications to the procedure. Rather than try to do them here, make sure you read your lab learning goals, because the specific amounts of materials that we're making are going to be different than are specified in your lab text. So you definitely have to read your lab learning goals, because we've adjusted both the procedure and the amounts. So you have to follow this video. This is where you get your mechanism, but make sure you've read the lab and you've read the lab learning goals to see how we're doing some things a little bit differently than they're described in the lab. Okay? I hope this has helped you prepare for lab this week. If you have any questions, make sure to ask. Make sure you're prepared for your lab work when you show up to lab next week. Thank you.